Welcome back to day 5. In the last lesson, I promised you that I'll show you a faster way of calculating the slope of the tangent at any point. Doing it from first principles is tedious, especially if the functions get more complicated. I just want to quickly review how to do it from first principles with these three functions to see if you notice a pattern. If we do it for x squared, the slope of the tangent, remember, is the limit as h approaches 0 of f of x plus h, so that would be x plus h squared, minus f of x, which would be x squared, all over h. So this becomes the limit as h goes to 0 of x squared plus 2xh plus h squared minus that x squared all over h. We end up getting the x squareds canceling, as we knew would happen. And then we end up with the limit as h goes to 0 of, if I factor out the h from the surviving terms, I end up with 2x plus h divided by h. And then the h's cancel. And as h goes to 0, this h goes to 0, I end up with 2x. Now, if we do it for x cubed, the slope of the tangent is the limit as h goes to 0 of x plus h cubed minus x cubed all over h. And hopefully you know how to expand x plus h cubed. And if you don't, you can always consult Pascal's triangle to give you the coefficients. But you'd end up with x cubed plus 3x squared h's plus 3xh squareds plus h cubed minus that x cubed on the end there, all over h. Again, the x cubes cancel, and if we factor out the h from the surviving terms, we end up with 3x squared h plus, oops, there's no h if I factor out the x squared, or the h rather. And then plus 3xh, because the h is gone, plus an h squared. This is all over h. The h's cancel. And we end up with, as h goes to 0, just 3x squared. Because this term will go to 0, and this term will go to 0 as h goes to 0. In the last case, the slope of the tangent is equal to the limit as h goes to 0 of x plus h to the 4th this time, minus x to the 4th all over h. And that's the limit as h goes to 0. I really should separate these things. And if we expand x plus 4 to the 4th, we end up getting x to the 4th plus 4 x cubed h's plus 6 x squared h squareds plus, the next one would be another 4 x h cubed plus, let's see what else, 1, and should be, oops, x cubed, sorry, that should be an x cubed, not x cubed. Let's fix this one. The x's are going down an exponent and the h's are going up, so this would be x h cubed plus an h to the 4th, and then we got that minus x to the 4th on the end, all over h. And once again, the x to the 4ths cancel, and all the surviving terms have an h in them, So if I factor out the h on the top, I get 4x cubed plus 6x squared h's plus 4xh squareds plus h cubed. And the h's cancel. And then if we take the limit at the same time here in the next step, as h goes to 0, this goes to 0, this goes to 0, this goes to 0, and we end up with just 4x cubed because it doesn't involve h. All right, so there's 3 of the certainly power functions, x squared, x cubed, next to the 4 done. Now, we just want to summarize this. So it says, observe the slope of the tangent to the following at any x was, for that, the slope of the tangent was equal to 2x. Here, the slope of the tangent was equal to 3x squared. And here, the slope of the tangent was equal to 4x cubed. Now, hopefully, by looking at the pattern of f of x versus the slope of the tangent, it says hypothesize that if f of x was x to the n, what would the slope of the tangent be? I'll give you 10 seconds to think about it. You can pause the video while you're thinking. All right, and assuming you've come back, hopefully you said that the slope of the tangent is n times x to the n minus 1. So you'll notice for all of them, if we bring the exponent down in front, so in the case of x cubed, a 3 comes out in front, and then you reduce the exponent by 1. So that's what's happened with all of those. Now, since the slope of the tangent can be determined by using a process, as we went through before, and now we found a faster way, certainly, of doing a power function, we're going to refer to this process as taking the derivative. And we'll call the resulting function the derivative function, because it's a function. 2 different notations are used to represent the derivative function. So one of them is Newton's notation, and he would have used f prime of x for the derivative, and Leibniz, which actually is a little bit more intuitive, wrote dy by dx. Okay, so this one is read f prime of x, and the Leibniz notation is read dy, so dy by dx, just phonetically, dy by dx. This kind of makes more sense intuitively because we're talking about slope of a tangent. Dy by dx is like a slope thing. It's like rise over run that you learned in earlier grades. And so this is just like, delta y over delta x, change in y over change in x. Okay, so delta y. So instead of using the delta symbols, we just wrote dy by dx. Now, the verb is differentiate, not derivate, even though the result is called the derivative function. The verb is the word differentiate. So we want to differentiate f of x equal to negative 1 over x squared. The first thing you might want to do is to write this in exponent form, so that there's, rather than in fractional form, we'll write it like this. And so f prime of x, using the Newton notation, says bring the n down in front, so this negative stays here, that times this negative 2, x to the negative 3. And so this ends up becoming 2 over x cubed. Now let's do this next question. So keeping this one in mind, that the derivative of negative 1 over x squared is 2 over x cubed, we're going to tackle this question. It says, Second, was there something below here? No, there wasn't. All right. So this time we're going to determine the equation of a line, which is called a normal, and that's a line which is perpendicular to the tangent to a graph. Now, f of x is equal to 1 over x, and you'll recall that 1 over x looks like this. It has the x-axis and y-axis as asymptotes, both in the first and third quadrants. And at x equal to 3, which might be, assuming this is 1, 1, so 3 would be about here somewhere. And so this point over here would be 3 and 1 over 3. But we're not interested in the slope of the tangent at this point. We are interested in the equation of the normal. So first I'm going to draw in the tangent. So the tangent might look something like this at that point. And the normal is a line which is perpendicular to that tangent. So it looks like, let's do this in different color. It would look something like, oops, I need the line here. So this line here, the black one, is called the tangent at x equal to 3. Whereas this line is called the normal. At x equal to 3. And that's what this question is asking us to do, determine the equation of the normal, which is the line which is perpendicular to the tangent of that curve at x equal to 3. All right, well, if f of x is equal to 1 over x, that would just be the same as x to the minus 1. And then f prime of x would be the derivative of this. So the negative 1 comes out in front, x, and then you reduce the exponent by 1, so that becomes negative 2. And so this ends up being negative 1 over x squared. And so the slope of our of the tangent is equal to negative 1 over, and this is at x equal to 3, would be negative 1 over 9. And so the slope of the normal, I'll write this as the perpendicular symbol, that just means the normal, would be the negative reciprocal of this, which would be 9. Right? The slopes of perpendicular lines are negative reciprocals. And so the equation of the normal then would be, we start off with y equals mx plus b, and we're going to sub in the slope of the normal into here, and sub in our point, which was 3 1/3. So we end up getting 1/3 is equal to m, which is 9, times x, which is 3, plus b. And so I get 1/3 minus this 9 times 3 is 27, plus b. That's 1/3 minus 3 times 27, that's 81, right? It's, yeah, 81 thirds. Oops, there's an equal sign in here somewhere. That should be an equal sign. And so b is just equal to negative 80 thirds. And so the equation is y is equal to m, which we said was 9, x minus 80 thirds. Now, minus 80 thirds is like, way down there on the y-axis. And you could see that would happen because this red line would continue going downwards and hit the y-axis quite far down, despite my graph being, relatively crude. Anyhow, so that's how you find the equation of a normal. Now, this is probably how you've learned to put equations of lines namely in slope y-intercept form. But on the AP exam, you may be required to give your answers in standard form, and so you probably should do that here. So to do that, I'm going to multiply everything by 3. So I end up getting 3y is equal to 27x minus 80. And so 27x minus 3y, I brought that 3y over, minus the 80 is equal to 0. And this is now in standard form. So a requirement for standard form, in case you don't remember, ax plus by plus c is equal to 0. And then there are some requirements here of this form. One is a over here must be positive. That's why I left the 27x there and brought the 3y over to keep the 27 staying positive. So the a must be positive. A, b, and c must be integers. You can't have fractions. And lastly, yeah, I said a is positive, so that one's fine. And the a, b, and c have to be in that order. Okay, ax plus by plus c equals 0. So that conforms to that. Now that we know how to do a derivative, or how to differentiate something, we need to discuss differentiability. This is just a theorem, and there's certainly no proof of it here, but I'm just stating it. Differentiability implies continuity. So if f has a derivative at x equal to some value, then f will be continuous at that. Okay, because remember what the derivative represents. It represents the slope of the tangent at x equal to a. So f then will be continuous at that point, x equals a. When will f prime of a fail to exist? Well, a function f of x will be differentiable if f prime of a exists. It's said to be differentiable on an interval if it's differentiable at every point in that interval. Now we're going to see some functions in a moment where they may be differentiable in some places but not others. And so a function is said to be non-differentiable at some point f of x if the slope of the tangent at that point is not defined. When can that happen? Well, 4 different reasons. One of them is if there's a hole in the graph, and we've seen that before, where you have, for example, a quadratic over a linear, and then the quadratic factored, and then the linear term and one of the quadratic terms cancels, and we end up at a hole at some point. So holes. Next one is asymptotes. Asymptotes. Because if the graph splits up, the region breaks up because of the asymptotes, it's not differentiable at that asymptote. Jumps. I'll draw pictures of all of these things in a moment. So where the graph jumps from one place to another. I'm talking about the y value here. And the last one, which we've not encountered yet, but you'll see very soon, are cusps and corners. Okay, these are grouped together. All right, now we're going to take a look at an example of each one of these things. The first one is, it says these are examples of non-differentiable functions at some point. It says consider the point 3 and f of 3. F of 3 would be 0. And so this function doesn't exist at x equal to 3. What does that correspond to? Well, this is a reciprocal function. It has a vertical asymptote at x equal to 3. So I'll draw that right there. And I'll leave it as red just to indicate that this is an asymptote. And then, of course, the graph simply looks like this and like this. And so at 3, the derivative is not going to exist because this is a vertical asymptote here. Hopefully that makes sense. Next one. X squared minus 9 over x minus 3. Well, this is an example of a quadratic over linear. top happens to factor into x plus 3 times x minus 3 all over x minus 3. The x minus 3's cancel. And so this resulting function is actually just x plus 3, which is linear. And that would look like this. At 3, so it looks like that. Just tidy that up a little bit because it would go through negative 3 on the x and positive 3 on the y-axis. So there's the line. However, at x equal to 3, right, we've made the assumption here, but when you do that canceling, that x cannot be 3. But if x was 3, y would be 6, according to this linear function. So f of 3, using this linear function, would be 6. And so at 3, 6, so 1, 2, 3, 1, 2, 3, 4, 5, 6, right there, there would be a hole here in the graph. Desmos, for example, if you plotted this, would not show you the hole, but I've used a program called MathGV, which you can get from, I may have mentioned this before, MathGV? MathGV. If you go to mathgv.com, that site is still up. It's very old. The young man who put this together does not maintain it anymore, but you can download the executable for MathGV. And if you use this to plot this function, x squared minus 9 over x minus 3, when it plots that line, you'll actually see a pixel missing on the screen where that hole is. So now you see an example of an asymptote and you see an example of a hole. Let's look at the next two. The first one is I call it C here, is root of 3 minus x. Now, if you remember your transformations, first of all, this graph only exists so long as x is smaller than or equal to negative 3. So at So at 3, let's see, we're going like this, and it goes like that. So it goes negative 3, so that would be right here, and going like that. And so x can be negative 3, because 3 minus negative 3 would be 6, and I can take its square root. X can't be, oh, I've got this going the wrong way around. Or do I? So actually the way to see this is this is the same as negative x plus 3. And so this is a reflection in the, let me just redo this again. I drew that on the wrong side. This is the square root function, which normally goes like that. The negative sign would make it go like that. And then the plus 3 says, did I do that right? No, that should be a negative 3 in here. Oh, look at the mistakes. So this should be x, whoopsies, x minus 3. And the x minus 3 from, is a horizontal translation to the left 3. And so we end up with it going this way. So let me erase these other ones here. So I did have it going the right way around. So it goes like that. Oh no, oh silly me. Negative 3 means it moved right 3, so it's actually over here. It goes like that. Oh, the mistakes today. Anyhow, so here's, this is positive 3. So that's what this graph looks like. Now, you might wonder, why is f prime not defined at 3? Well, if you take a look at the tangents, the tangent over here would be, something like that. And then as we get along here, then it looks like that. And by the time we get up here to, we get to the end here, it looks like that. We end up at 3 being vertical. And you can't have a vertical tangent like that. And so we say that f prime of x is not defined. It's not defined here. Okay, this is an example of what's known as a cusp. Cusp. I'll show you another example of a cusp. In fact, maybe I'll just do that right now. If we took a look at the function f of x equal to x to the 2/3, for example, you'll see that the function looks like, well, let's go into Desmos and plot it so you can see. And if I plot x raised to the 2/3, you can see what this function looks like. So I'm just going to go back into my lesson here and draw this in a different color here. So this one looks like this and like that. So this is the graph of f of x equal to x to the 2/3. And the same thing is going to happen here. Going from left to right, you can see how the tangents are getting larger negative. But then as soon as we hit that point, they start turning positive, and we can't have a derivative or slope of tangent changing drastically like that at a point. And so this is called a cusp. Okay, all right. So that's cusps, and we haven't looked at corners, but we will in a moment. This is a piecewise function. And so it says it looks like 3x minus 1 so long as x is less than 3. Well, 3x minus 1 looks like something like this. Oops, no, 3x minus 1. Something like that. It has a slope of 3 roughly. I haven't drawn this perfect, but it only looks like that for x less than or equal to 3. So what I'm going to do is to just change this. So when it's 3, this would be 9 minus 1, which is 8. So this, oops, let's fix that. So this point over here would be at 3 and 8, which would be about here somewhere. And this would probably be a bit steeper like that. It has a slope of 3. And it says f of x is equal to 1 for x's which are bigger than 3. And so at this point, what does that look like? Well, x equals 1 is just a straight line. So it goes from here to there onwards. Right, so this graph goes like that. And this was strictly greater than 3, so there's a hole here, but that hole is filled, of course, by this function up here. So here's an example of what they call a jump. So this is a jump. And so f prime of x is not defined. At x equal to 3. Okay. Next, I'd like to take a look at what's called a corner. You'll recall that absolute x, y equals x so long as x is positive, and y f of x is equal to the negative of x if x is negative. So we end up we get this line. So that's what absolute x looks like, f of x. Well, you can see that the derivative on the left-hand side of the y-axis is -1, on the right-hand side is +1. So again, it's changing drastically at the origin. And because of the change in slope drastically at the origin, we say that f prime of x does not exist. I'll abbreviate this to D and E, does not exist at x equal to 0. Okay, so at x equal to 0, this is called a corner. Oh, I'd forgotten that I'd done this already. Here's the cusp. This is the graph of 3x minus 6 raised to the 2/3. So that's a cusp. And so as stated earlier, this function would not be differentiable at 2. So we'll talk about how to do the derivative of a function like this later on because it involves a little bit more stuff. But so you'll have to hang in there. Now, that kind of concludes this introduction to taking derivatives. Just as a sort of point of interest. Oh, before I forget, it says just because a function is not differentiable everywhere, doesn't mean you can't take its derivative. You might be able to still take the derivative, it just doesn't exist in certain places. Now, as I was trying to say, just as a point of interest, in case you've ever been asked to prove something, you know that if you try and prove something, you can't do it by example. And here's a perfect example. If n happens to be equal to 1, this has got nothing to do with calculus, by the way. This is just a point of interest. If n is equal to 1, I put 1 in there, I'll get 1141 plus 1, which is 1142. And if you take its square root, you'll find it's not a perfect square. Okay, so I'll say no. And if n is equal to 2, you get 1141 times 2 squared. So that plus 1, that would come to 4565. And if you check, this is not a perfect square either. And if you check 3, you'll get 10,270, and it's not a perfect square. And if I put 4, I get 18,257, and it's not a perfect square. And so you might think that, gee, maybe this formula 1 plus 1141 n squared generates non-perfect squares. And you could keep going like this. And you might make the hypothesis that 1 plus 1141 n squared never generates a perfect square. Well, if you made that hypothesis, you'd be wrong, because this number, I don't know even how to say this, but here we've got thousands, we've got 197 million, billions, trillions, quadrillions, pentillions, sextillions, I think it's heptillions. Anyway, if you put that number in for n, square it and add 1, lo and behold, it's a perfect square. Generates a perfect square. So the point of the exercise is, when you're asked to prove something, you can't do it by example, because it might, in this particular case, works up to 30 heptillion and change. But after that, one more try, and all of a sudden this number generates a perfect square. I just thought I'd point that out just for interest. Here's another thing that might interest you. I'm sure you've learned that x squared plus y squared is equal to z squared. This is well known. This is just the Pythagorean identity. And there was a long-term problem that was stated that had remained unsolved for over 400 odd years. And that is, what happens if that exponent there becomes a cube? Like, is there some solution to x cubed plus y cubed equal to z cubed? Is this a solution to x to the fourth plus y to the fourth equal to z to the fourth? And so on and so forth. In other words, are there solutions to these equations for n greater than 2? Well, as it turns out, the proof for this took a long time to produce. The problem was known as Fermat's last theorem. Fermat being a French mathematician. Fermat's last theorem. And Fermat had stated that he knew that there are no others, none of these would have solutions except for the Pythagorean one. And the story goes that he had a proof, but he said, I just don't have room in this margin here to show the proof. And so he left it. And he left a number of theorems unproven, and almost over the hundreds of years that followed, all of his proofs were proven except for this one. That's why it's known as Fermat's last theorem. And then back in, I think, 1991, I could stand to be corrected, but a man by the name of Andrew Wiles solved this. And he proved that there's, beyond the Pythagorean one, there are no solutions. Fermat couldn't have had a solution, certainly not the one that Andrew Wiles provided, because his proof was like over 400 pages. text, of typewritten text, and so, which he did on a typewriter, by the way. If you ever get a chance to take a look at the movie The Proof, I used to show this in my Calculus AP classes, if nothing else, to interest kids on the passion that Andrew Wiles, so this is Andrew Wiles, this is how he's, Wiles, I believe he was a professor at Princeton, I believe, in New Jersey. He is the one that solved this, and he provided the proof on a chalkboard. He's old school, at Cambridge University, where Sir Isaac Newton was a chancellor. I happened to have the opportunity, because I'm a bit of a math nerd, I went up to Cambridge and went to the library where Sir Isaac Newton's death mask is, and also in that library is a classroom where Andrew Wiles provided the proof for Fermat's last theorem. So if you ever get a chance and you're in Cambridge, you might want to check that out. And also check out this movie called The Proof. Great viewing if you love mathematics. Take care. Bye-bye. And that's it.